Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Lauren Tetzlaff. Lauren is a thermal and CFD engineer at Thermal Analytics who works closely with our customers to provide support throughout their projects. She specializes in cabin and underbody simulations while also assisting the software development team by providing input on new features. Lauren has been with TAI since 2015, when she began as an intern while obtaining her bachelor's degree in mechanical engineering from Michigan Technological University. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. And we are also recording this webinar and we'll be sending you the link following this presentation. And with that, Lauren, if you're ready, you may begin.
All right, thank you, Chris. Hello, everyone. The topic of today's webinar is Unlocking Solar Insights, TAITherm for Accurate Thermal Modeling. We'll just start out with an outline to see what we'll be covering with today's presentation. We'll start out with some motivation, and then we'll look at 5 different application examples, both from architecture as well as some vehicle examples. We'll briefly look at some automation possibilities with CoTherm, and we'll finish with conclusions. First, solar loading is powerful. These are some recent headlines that have been shown with just how powerful solar loading can be. A lot of these examples show vehicle components melting or failing because of being parked next to buildings that have some type of solar glint that is concentrating high solar loads on the vehicles. So a couple different examples, a car in a driveway. We also have examples from different cities where things like this happen. So again, solar loading is very powerful. And solar is also complex. Solar direction and intensity change throughout the day. Different environmental factors influence our product of interest. The material properties affect the thermal results. And location matters depending on where we are on the globe. That's going to change our solar loading. However, modeling solar doesn't have to be. Within TAITherm, we include environmental effects with a weather file, which can be from any location. We include solar, direct, diffuse, and reflected. We can see in this little schematic here, we have solar reflections, which are both specular and diffuse. We have incident solar, direct and diffuse, and then we also consider radiation exchange with the sky, as well as wind convection with the natural environment. Just a brief overview of the different software packages that Thermal Analytics offers if some people on the line are not familiar. So we have TAITherm, which is the flagship thermal software. That's what all of the simulations in today's webinar were run in. And then we also have MUSIS, which is the infrared signature simulation software. With both of these packages, we have a number of different extensions that can be used with them. We have battery, human thermal, exhaust, and rapid flow. We will be using human thermal for one of the examples today. And then we also have CoTherm, which is multi-physics co-simulation. And with that, we also have the drive cycle extension, which can be used with CoTherm. Since our examples are in TAITherm, just a little more information on that main piece of software. TAITherm computes heat transfer. It predicts temperatures. It can be run in transient and steady state. It includes convection, conduction, and radiation, as well as natural environment. And that natural environment piece is the piece that we're focusing on today, since we are specifically interested in solar loading. Let's take a look now at our examples. So first we'll start with 2 architecture examples. The first of which is a concave glass building, and we want to look at the building effect on parking lot vehicle temperatures. The setup for this model is a glass building in the sun. So we can see that we have this concave glass building, and then we have a parking lot in front of it with a number of vehicles parked in that parking lot. And because of the curvature of the building, we can get an increased solar loading on the vehicles in the parking lot. This particular image is showing us temperature. So we can see that we have some concentrated temperatures on that center vehicle in the front row, especially on the hood of that vehicle. We can also look at an animation of solar flux. So as the solar is moving throughout the day, we can see that those reflections are changing. And then they concentrate on the vehicle, specifically that center vehicle, around the middle of the day. And so that elevated solar flux and those reflections, that's what's causing the elevated temperatures that we saw in the previous image. Now with our software, we can try different glass properties easily to be able to see what effect that would have on the simulation results that we're interested in. So in this particular case, we just quickly changed the glass property from what we're calling this original glass, which had the very high temperatures, to a less reflective glass. You can see that with the less reflective glass, we significantly lower the temperatures on the hood of that vehicle. Now with this, we would also want to consider, what's happening to the people inside the building. And we'll look at that a little bit more in our next example with a different architecture example. So just because we change the glass, to help one side of the equation, we'd also want to think about the people working or living in that building and what effect that would have on them. So we'll look at that kind of interior effect with this next example. This is a glass office building, and we'll look at some different interior temperatures with different glazing materials. So with this, we have the building geometry, as we can see here. We have normal glass, which on the left-hand side, all of the blue color. So you can see a lot of the building has these big windows that are covered by this normal glass. And then on the right, we're changing that out to be a more reflective glass. That's that light green color. So we changed all of the windows, just not that glass railing, to be that less reflective glass. And then we can see what effect that has on our model. So here we can see the net solar flux on the building. This particular model was done in Phoenix, Arizona in the summer. It was started very early in the morning. That's why we're not seeing the solar flux initially, but then we're seeing that build throughout the day and then also move across the sky. So here we can see the difference between the two glass types. In this image, the glass is hidden so that we can actually see the net solar flux looking through the glass inside the building. So the net solar flux is higher with the normal glass inside the building than it is with the reflective glass. We can also look at this from a different perspective. So this image is taken as if we're standing in the building and then we're looking toward those windows. So we have that same shadowing of the net solar flux through the windows. And this is just to see the values in a graphical form. So again, we can see they're pretty consistent until we get to the point where the sun is really kind of shining through those windows. We can see that uptick near the end of the simulation. And again, we can see that with the normal glass, we have much higher net solar flux than we do with the reflective glass. And then we can also look at surface temperatures. So we saw that the net solar flux was higher with the normal glass. But with surface temperatures, we see a couple different things here. So the floor surface temperatures are higher in the normal glass case. If again, we look at that shadow kind of on the floor directly behind that window. However, the windows have a higher temperature in the reflective glass case. So we have a few different factors here that are kind of competing against one another. What might be interesting as an extension to this model would be to add a human representation using our human thermal extension to the model to see how those different effects would affect human comfort, since they'd be a little bit competing. We'd have the higher temperatures in the reflective case, which would cause a higher radiative load on the human, but we'd also have lower solar. So it would be an interesting extension to the model. And then finally, we can also look at air temperatures inside the building. And this building was just using some simple bulk air temperature representations, as you can see in the graphic. So we just have one air temperature for each floor. And then we can look at those between the two different cases. This model was run using a simple representation of an AC, which is a fixed negative 1200 watts applied to those different air temperatures. That starts around 8:30, which is why you see that little inflection point on the graph. If we look at the end of the simulation, we can see that the normal glass air temperatures reach a higher value at the end than the reflective glass. So the reflective glass does also lower our air temperature, which if we were targeting a certain air temperature, that could help with energy consumption because we could use less energy to maintain the same air temperature. Next, let's look at some vehicle applications. The first one we will review is a cabin comfort application, where we will look at the effect of glass properties on power consumption in a vehicle cabin. So first, let's look at the model setup. So we have our vehicle that has a number of different glass surfaces. We have the windshield, the side windows, a big sunroof on the top, and then our rear windshield. And these will be the surfaces that we will change between the two models. Then we have our two different glass types, just the details about those. And this model again was run in Phoenix, Arizona in the summer so that we can have high air temperatures and high solar loading. This model does include using our human thermal extension, and we're using 4 50th percentile humans in this model. There's clothing applied to these humans to all areas besides the face, head, neck, and their hands. And in order to run the human simulation, we do something called a precondition, which is just to run the humans before they enter our model of interest. So our model of interest is when they're in the cabin. And before that, we have them engaging in some light walking. And then when they're in the vehicle itself, they're going to be sitting and relaxed. The cabin itself will also have two different models that we run. First, we run a solar soak. This is going to be our hot soak, where we have the high temperature and the high solar loading. We have no cooling power applied, and this is the vehicle only. So this is just the vehicle sitting in the hot sun. After we run that, we will then follow it with our AC cool down. This is the same environment as our soak, but this is where we're going to apply the cooling power, and we'll also add the humans into our model. So first, let's just look at some results from the solar soak. Here we're looking at solar flux, and we can see the difference between the standard glass and the reflective glass. So again, like we were seeing in the architecture example, with the standard glass, we have higher solar flux than we do with the reflective glass inside the vehicle. And just to be clear here, the windows are hidden in this view so that we're seeing the solar flux inside the vehicle kind of through the windows. So next we have the cool down model. For this model, this is using a simple fluid network within TAITherm, and it uses a sensation-based imposed negative heat rate. This is done using a PID controller. And if we follow the schematic at the bottom here, we can kind of see how this is done. So our model will report driver thermal sensation. That then is used as an input to the PID controller. The PID controller then sees if that sensation is above or below neutral, and then will give a new imposed heat to the heater fluid node based on that input. That imposed heat is then going to change the cabin air temperature. That cabin air temperature is then going to affect the driver sensation, and we will continue that loop until the end of our transient simulation. What this allows us to do is compare the overall imposed heat between the two designs to be able to determine power savings. So let's look at these two models. Here we have the glass hidden again, but here we're looking at the surface temperatures. And we can see that these are fairly similar between the two models because we are applying cooling, but we can see some key differences if we look at the dash. The dash in the standard glass case is still warmer than with that solar reflective glass case. So let's look at the air temperatures. We can see that the solar reflective glass case ended about 2 degrees higher than the standard glass case. And that would lead to the question, why does the solar reflective glass case result in a higher air temperature, even though we're using this controller? So the solar reflective glass allows less incoming solar radiation, so that humans can tolerate a warmer air temperature while still maintaining the same thermal sensation as the standard glass. So again, we're targeting the same thermal sensation, not simply an air temperature. So that's why we see that difference. We are maintaining the same sensation. It just, again, the humans can tolerate that warmer air temperature because they have less solar coming in and hitting them. And then finally, we'll look at the power consumption. So we can see that the power consumption with the solar reflective glass is less than the standard glass. Again, if you look at the units of power here, kind of a higher line is actually less because it's closer to 0. So if we look at just the study, so just looking at the very end of the graph near 60 minutes, the power saving was 18% for the solar reflective glass compared to the standard glass. And then if we include the entire 60-minute duration, the power saving was 21%. So a little bit higher transient than with just looking at the study. The next example that we will look at is a derating example, where we'll use TAITherm to assess component temperatures under high solar loads. So just a little bit of derating background. Derating carries some risks of features being disabled when a certain temperature threshold is exceeded. This can happen in many different components in a vehicle, such as ECUs, infotainment centers, sensors, cameras, antennas, headlamps, and tail lamps. And then in this little schematic, we can see that there are certain temperature ranges where different things will no longer work. So with the radio, you have a safe zone, then you kind of get into this orange zone. And then finally, if you exceed a certain temperature threshold, you will then have no radio. So we have a simple model just to look at how we could kind of assess these boundary conditions, see if these components are getting too warm using simulation. So in this example, we have a radio module, which is located below a roof antenna. So you can see on the vehicle there within the shark fin, we then have this radio module that is sitting below that. And this model is a soak model, which is modeled in a hot summer condition with high ambient and high solar loading. So if we run this model, we can then look at the surface temperature of our component. So again, zooming in on the electronics underneath of that shark fin, we can see the surface temperatures on the vehicle as well as the radio module, which can all be visualized in TAITherm to see if we are exceeding certain temperature thresholds for those components. This is just looking at some different surface as well as fluid temperatures. There are different air temperatures that are modeled within the shark fin and then within the roof cavity. So we can see that the roof cavity becomes the most elevated, reaching almost 70 C. We then have the fluid within the radio module, which again is the air temperature within that module, and then the module itself. So we could use this information again to compare it to see if we're reaching any of those critical points where something would stop functioning. Some future work in this area could be to add some additional drive cycles to model in addition to just simply a solar soak. And we could also add additional component details, such as looking at different electronics installation, heat sinks for the cooling, as well as a fan for electronics cooling. The last example that we will discuss today is transparent photovoltaics for vehicle integrated photovoltaics. We'll look at the annual energy production comparison based on the surface area covered in these TPVs. So TPVs for VIPVs, transparent photovoltaics for vehicle integrated photovoltaics. So TPVs selectively absorb different UV and IR wavelengths while transmitting visible light. This could allow for harvesting solar energy from automobiles without impacting the function or the aesthetics. In this image, we just see an example of what that could look like with one of these VIPVs integrated onto a sunroof. So next, we'll talk about the methods for modeling this. We model this using a coupled thermal-electrical modeling approach. PV performance can be strongly dependent on temperature, therefore we need a coupled thermal-electrical approach. Using TAITherm, a workflow was created that solves the PV electrical equations using Python at the end of each thermal simulation time step. And there's some more details on that workflow in the diagram on the right. So we're going to use that approach to compare 3 different modeling scenarios to look at the annual energy created by these different approaches. So model 1 is using a conventional mono-Si rooftop module, and the surface area of this module is 2.8 meters squared. In the image there, it's that gray portion of the vehicle covering the entire roof. The second model is using TPV films installed on the windows only. The surface area of all of these windows is 5.54 meters squared. And in this image, it's all of the pink. So we have a sunroof in this model, as well as all of the traditional window placement. And then finally, we have TPV films covering the vehicle's entire external surface area. So that would be all of the light pink in the image, as well as that darker magenta color. And this surface area is much higher, coming in at 16.45 meters squared. In these 2 models, the TPV films are modeled using an estimated achievable efficiency of 15%. And then also the spectral properties as shown in the 2 graphs. So from running these models, we can then compare the annual energy production for different levels of PV coverage on vehicles, as well as different locations. The weather for these vehicles was taken from a TMY data from the NROL database. So we can see that the full coverage, as expected, has a lot more annual energy production than the other 2 models. It had the highest surface area of PV coverage. Next up are the windows only case, which is slightly higher than the silicone PV roof. The windows only case did have a higher surface area, although a lot of it was on the side windows, so those don't have as good of an angle toward the sun. But including the sunroof, we did have a higher overall coverage area, so they did produce more energy than just the PV roof. And looking at the different locations, we can see that places that have higher sun, higher solar loading are going to have more energy production than areas with less sunny days and less intense solar. We can then convert this into driving range. This was converted using an assumption of 26 kilowatt hours for every 100 miles EV efficiency. So then we can look at those 5 different locations for the different coverage options. Again, the TPV coverage is going to be the highest, followed by windows, and then followed by the SIPV roof. Next, we'll look at a few different options for automating with TAITherm. So sometimes when we are modeling these different solar cases, we may want to add some automation in if we want to look at multiple locations, like in that last example. So maybe we don't just want to run one location, but we want to run many locations. We could automate this by providing a folder that has all of these different weather files, and then having TAITherm easily loop through these different weather files and outputting some information to us that we want to look at by adding in some automated post-processing. This can be beneficial to understand the effects of range of weather, not just a worst case scenario. TAITherm has multiple options for plotting, surrogate modeling, and sensitivity analysis, and these would all help us to run and analyze many iterations of scenario, weather, and material properties. Another way we could use TAITherm would be to run a DOE of different glass properties. So maybe we have, one environment of interest, but we want to see how changing the glass properties would affect our result of interest. So in this simple example, we're just showing that you could change the glass reflectance and the glass transmittance, and then run a DOE where TAITherm would take care of updating all of those glass properties for you, looping through all of those models, and then outputting important results. This would allow you to study the impact of different properties on components of interest. Finally, we'll wrap up with some conclusions. So in conclusion, solar heat is a complex 3D phenomenon. Understanding these effects efficiently requires fast 3D simulation and analysis techniques. A robust simulation and analysis process will allow you to predict and mitigate design issues related to solar heating and thermal management early in the design process. All right, and that wraps it up for today. So thank you for attending, and we'll open it up if there were any questions, Chris.
Yeah, thanks, Lauren. So first question here, how do you input a new glass property into the model?
Yes, so you need transmittance and reflectance. Those can be either values or curves. And then you also need the thickness that the sample was measured at.
All right, thank you. Next question, isn't it important that glass properties, especially for solar loading,
I'm sorry, Chris, I missed the last part of that question. Could you please repeat that?
Of course. Isn't it important that glass properties, especially for solar loading, should have multiple bands?
So TAITherm uses a two-band approach where it splits things from very high bands and very low bands, and that's going to be based on what the properties were measured at. So when you input the transmittance and the reflectance, if you input a curve, you can also input your spectral source curve, which is then going to be used to determine what those glass properties are. So yeah, there's different ways to input those. And again, TAITherm uses the two-band average approach. And we've got a good FAQ on that. I could include that as well for some more information about the two-band approach.
Awesome, thank you. What is required to configure the sun motion in the model?
Yes, so there are two different options to get the sun motion. You can either have TAITherm calculate it by providing the global position. And the global position, you need the latitude and longitude as well as your time zone. And that allows TAITherm to then calculate, where the sun is going to be. Or you could provide it. So if you have a weather file that has the environmental parameters, including solar loading, so you'd need the solar loading, and then you'd also need the azimuth and zenith angle. If you have that information, you can also just input it into the software, and then TAITherm would use that data.
Okay, thank you. Well, it looks like that'll do it for questions. So thank you, Lauren. Thank you, everyone, for attending today. We appreciate that very much. We will be sending you a link in a little while here with the recording of today's presentation, as well as a copy of the slides. Again, thank you, Lauren, and everyone have a nice day.
All right, thank you, everyone. Have a nice day. Bye-bye.